You guys are like, me too. Oh, videos get your money's worth. How much you paying for them? Nada. All right, let's talk about, first, are there any questions? Everything's going well? You learning? All right, I want you telling your other classes you're learning nothing in 620, 420. Is he joking or serious? Who knows? Who cares? All right, let's talk about supply-independent biasing. So you remember when we did this and we calculated the current that flows, then we use this to bias other current mirrors? Does anybody remember? And so a lot of times when you look in industry and you look at how they design stuff and what they write, they won't show you this part of the circuit. It'll just be somewhere else on the chip. And they'll just call this, say, V bias N for biasing the NMOS. And this is a bias voltage that they will route to a specific section like an op amp or a data converter or whatever. And they will use that to bias current mirrors. So you might have a whole string of current mirrors. But the problem with this is that if VDD goes up or VDD goes down, it directly changes the current. So if I were to plot the current that flows through here, and I were to, and I probably have a figure in the book, but plot VDD versus I would probably get something that looks like this. And a lot of times you don't want that. You want to have the currents stay constant with temperature and with power supply voltage. So before I go any further, I'm going to pause and I'm going to show you a circuit that's useful in like driving a monitor. Okay, so like a digital display like HDMI or DVI or one of those. And it's built with current mirrors. And so what we have is the following. If I have in the monitor, and I'll draw this a little different, but if I look at the input to the monitor, and these are a little bit more, no, it's a lot more complicated nowadays, but you might have this. You might have 75 ohms and 75 ohms, and those are the two loads that you have to drive in the monitor. So you measure the impedance and you get 75 ohms, and you get a plus node and a minus node. And the reason for that is that when you transmit a signal on a wire, the wire behaves like an antenna. And it will pick up noise. It'll pick up radio waves. It'll pick up television waves, okay? So what's done almost at everything, even high speed in cell phones, is that signals that are high speed are not transmitted with one wire. They're transmitted with two wires, one that's called data plus and the other that's called data minus. So when this one's going up, this one's going down, so they're complementary, okay? And then you get the noise on the wire. Then when you get over to the receiver, like right here, there's a circuit that will, a diff amp, that takes the two outputs and subtracts them. So any coupled noise, like from a television station or a radio station, is subtracted when you take the difference. It's only the difference mode signal that gets into the circuit. So these signals are transmitted differentially. Has everybody got that? So you want the picked up electromagnetic radiation to be coupled evenly into both lines. So when I was a kid, you would have a TV and there was no such thing as cable or whatever, and you would put an antenna on the TV, and then to get it to work, you would take some tin foil or you take like a hanger and you bend it all around to try to get reception on the TV so that you could get the TV channel. And it's the same thing here. You have a long wire, it's going to pick up information, and it's going to pick up the radio waves and have noise, or when I say noise, everybody knows that's an unwanted electrical signal, okay? So I'll be curious if anybody's seen this. So if you were to look at the back of the TVs, the older TVs, they'd have like two lugs here for the receiver, and then you might have an antenna on your roof or an antenna some other place, and the piece of cable that would come in, and it was a flat plastic ribbon cable where they would keep the wires spaced a certain ways apart. And this was how you fed the signals into the TV. It's this flat piece of cable that went into the TV. And it was a rigid plastic, and it would go all the way up to the antenna. And the antenna would be like this, and it would be picking up and tuned to send radio signals down to your receiver, and then it was spaced out evenly like this, so hopefully the same unwanted signals would get picked up, and only the different signal picked up by the antenna would be amplified by the TV, okay? All right, so anyway, you have these plus and minus circuits. So I'm just going to draw this. This is in the monitor, actually, the monitor. And we're going to make what's called a digital to analog converter. And I know if you took, there's a few of you in here that have taken 421, the digital class, and we did a digital to analog converter in the lab. However, I'm going to do a different one since this is analog. Okay, so what we're going to do is the following. If I take this PMOS, and this all should look familiar from your homework assignment, and I bias it, so this has 10 microamps. Okay, then I come over here, and I make this the same size, except here, what I'm going to do is I'm going to put another switch in series here that's active low. So I'm going to call this bit 0 bar. And it's going to be ultimately connected to the 75 ohms in the speaker, or the monitor. Okay, so let's make sure we know how this works. If bit 0 bar is a low, what's the state of this transistor? It's on, right? It's a wire, it turns on. Does everybody agree with that? Bit 0 is a bar, this turns on. So when I say bit 0 bar is low, it's just because I have phobias about your digital classes here. What does that mean? What is the voltage on bit 0? What is the voltage here if I say bit 0 bar is a low? 0. Okay, bit 0 bar is a low. Bit 0 is a bar. Bit 0 is a 1. Bit 0 bar is a 0. Okay? And so then what happens is this signal here drives 10 microamps into the 75 ohms, and I get 75 microvolts. Then I come over here, and I make this M equal 2, or 2 in parallel. And I get 20 microamps, and I come over here, and I call this bit 1 bar, and I tie it in. So both bit 0 bar and bit 1 bar are low. What's the total current going to the 75 ohms? 30. But if only bit 1 bar is low, what's the and this one's high, this switches off. And what's the current going into the load? 20. And you can imagine I can keep going on there. And there's tricks to doing this where you don't have to keep multiplying up. And this would be bit 2 bar, and this would be 40. And so if all three were going, I'd get 70 microamps. If none of them were, I'd get 0. And so you can imagine going up, and then by adjusting this digital word, I can then get an analog voltage here, which is the currents times the resistance, and this is called a DAC, or digital to analog converter. We all follow. So now imagine we're using this DAC, and for whatever reason, the power supply drops a little bit. Okay, power supply drops a little bit. What's going to happen to my currents then, my 10, 20, and 40 microamps? They're going to go down. What's going to happen to the intensity of the signal that I have in my monitor? Go down. And so what I'm saying is I'm saying that the power supply is dropping, and my monitor is getting dimmer. I don't want that. I want my monitor to stay at the same brightness. So I've got to come up with a way where instead of having the resistor here in the drain side of the circuit, I have the resistor some other place, or some other way to bias this. Does everybody see the problem? so that the current doesn't change with the power supply voltage. And ideally, it doesn't change with VDD, with temperature either. Any questions? Okay, so here's how we're going to do it. This is called supply independent biasing. What this resistor is supply dependent biasing. The biasing depends directly on the VDD. When I look at this, I can't solve for the current without using VDD. What I want is a circuit that I can solve for the current and there's no VDD in the equation. Okay, so here's how we're going to do it. Instead of putting the resistor on the drain side, I'm going to put it on the source side. So I'll do something like this. And of course, if I have a current mirror here, and this generates a VGS, if I make these two the same sizes, the only way that this current and this current can be the same is if this node is at ground. But if this node is at ground, then no current's flowing in the resistor. That's bad. So what I'm going to do is I'm going to make this wider. I'm going to make it M equal to 4 so that this VGS 2 is less than the VGS 1. So VGS 1 is greater than VGS 2. But I still have to force the same currents through each side. So the way I'm going to do that is the following. I'm going to put a current mirror up here. Like this. So that the current flowing in this side is equal to the current flowing over, is mirrored over here. So now, I'm going to ask you some really simple questions. What is this voltage here? VGS 1. But you told me that the voltage between here and here is VGS 2. So what's this current? I mean, what's that voltage? I'll start out. VGS 1. Now you see why this has to be wider. If it's not wider, then this VGS isn't less than VGS 1, and the current that flows is 0. Everybody got that? Make sense, Luis? So this voltage is VGS 1. So this voltage plus to minus is VGS 2. So this is wider. So for the same current, because it's wider, its VGS 2 has to be lower. So this VGS 2 has to be less than VGS 1. Okay? Does that make sense? Don't lie, man. So if this is VGS 1, well, wait, you see that these are the same size, so the current flowing here is I, the current flowing through here is I. That sets a VGS 1 here. But I made this wider. So if it's wider, for the same amount of current, won't the VGS 2 have to be lower? Because remember, I equals Kp over 2 W over L VGS minus V threshold N squared. And so if I make this W bigger, I multiply it times 4. In order for the currents to go the same, the only other variable here is VGS. Doesn't the VGS have to go down? Henry?
My question is, if you connect any side over here, the left circuit, would that be pulling VDD to ground?
No, because let's just put some numbers in. Let's say VGS is 1, and this voltage is 0.9. Okay? So that means there's 0.1 volts across here, right? Let's say this is 5. Well, this is still 1. Let's say the VSG is 1.1, so that this is 3.9. So the drain is at 3.9. The gate here is at 1. This voltage is 0.9 because I made it wider. And then this is 0.1. And then this voltage, I just have a voltage here of plus minus 4 and a voltage here of plus minus 1.1. Okay, so let's do it again. Hisham. See, I remembered. I don't like the way you spelled it, though, because I have another Hisham in my class, the previous, but he spells H-I-S-H-A-M, which I can understand. All right, Let's say this drops to 4 volts now. What does this voltage change to? Nothing. It's still 1 volt. Well, what does this voltage go to? 2.9 because it's 1.1 volts below 4. What does this voltage change to? Stays at 0.1. So by varying the voltage, I'm just varying the voltage on this node here and the voltage between the source and drain, but this stays at 1 and this stays at 0.1. Mo? Good? Anthony C?
So would that change from the drain to source voltage on the 4 transistors in parallel? Is that like, does that have a very minimal effect on the current?
Well, it depends on the output resistance, right? It's not going to, if their output resistance was perfectly flat, these wouldn't change, but in reality it's not. So it's not going to be perfect that the current won't change with VDD, but there's tricks that you can do to make it so that it's near perfect. Okay, we'll talk about later. Okay, but does everybody understand what I'm doing? Forcing the same current through both sides with this circuit, PMOS current mirror. Making this transistor wider so its VGS is less than this one, and then dropping the difference between this VGS and this VGS across the resistor. So that my current, then, I can write as I equals VGS1 minus VGS2 all over R. Or I can write it as VGS1 is the square root of KP over 2, is equal to 2I over KP W over L minus V threshold N minus the square root of 2I over KP times M times W over L minus V threshold N. What happens to the differences in threshold voltage? They cancel. So if I have manufacturing variances, the threshold voltage, it doesn't influence my current. So I'm going to rewrite this as I, just doing algebra now, is, what's that? Oh yeah, over R. Over R. Oh, that's over R. That's equal to, I'm going to move that inside actually, 2I over KP times W over L times R squared times 1 minus 1 over the square root of M. Who agrees with that? Might better if I put it up. Sony? So 2I KP W over L, that's factored out, leaves a 1. 2I KP W over L is factored out, that leaves M. I move the R inside, I get R squared. And so I've got just this term right here. And in the book I used K for instead of M. Proceed or stop and question your choice in taking 420. It's too late. I'm sit here and I watch, and whatever's in that classroom there, people just constantly go in and out, and I think, how nice. Like, nice. All right. Okay, so does everybody agree with this? Does anybody agree with this? All right, Kayla agrees. Chris? All right, so I got I square root of I. So why don't I square both sides and then divide the I out? So if I square this side, it's I squared. If I square this side, it's 2I KP W over L R squared times this squared. Then I divide the I here and the I squared. And I end up with I equals the square root of 2 over KP times W over L R squared times 1 minus 1 over square root m. Does anybody agree with that? Oh, squared. Thank you. And yeah, thank you. Better? Victor P., you good? All right. So now, let's just say, for example, m equals 4. What does this become? Right? And then what is 1 minus 1/2? 1/2. Anybody agree? And then if I say, okay, well, what is that? That would be 1/4. You all agree with that? And then I can plug that and do a cancellation here. And I get I, and I've got a little mistake, I think. Pull out the book. I've done this a few times, so I know when I've got an issue. Oh, so long. Matching. All right. Okay, so let me just show you where we are in the book. We just arrived, and again, I used K. And so we got to right here. For m equal to 4, that's 1 over 2. 1 minus 1 is 1/2. Okay. All right, I'm having a brain fart here. Why did... okay, so I did do it right. So that's right. What's that? Here? I think I did it right. Yeah, I did it right. Why am I having a problem here? Because I'm making problems where there aren't any. That's why. All right, so for m equal 4, what do I get? I get 1 over 2 kp w over L times r squared. Does anybody agree with that? Okay, and what is the value of gm equal to? One of them, square root of 2 ID if we want, kp w over L. Looking good? So now, couldn't I write that r squared equals 1 over 2 ID times kp times w over L? And wouldn't that mean, this is for k equal to 4, or m equal 4 in the book, wouldn't that mean that r is equal to 1 over the square root of 2ID kp times w over L? Did you just leave my room after I made comments about people leaving? It's only been a half. Mental note, never go on road trips with my students. I need to stop and use the bathroom. What the hell? You're never gonna get there. All right, 1 over GM. So by doing this, setting k equal to 4, I can set my R will be 1 over GM. Any questions? So let's see it work, shall we? So what's the point of this circuit?
So that we can have the same current mirrored and it's a VDD.
Yeah, we can set the current and the GM based upon the resistance. So this would be, and crap, I think I got to download the LT Spice folders again because he keeps changing it, and so I'm going through and checking for issues. And I guess you can't complain when it's free. Okay, so this is (2016). Extract here. Oh, I should have done this earlier. Oh. So what I'm going to do, this is the long channel, and we're going to see. Actually, you know what? Before we even do that, let's do one more thing. I want you to estimate the minimum using the C5 or the 1 micron book process. I want you to help me estimate what the minimum voltage VDD can be, and it still work. Okay? So here, this will be something we'll do. So I'm going to just say VDD min. So I bias for a particular VGS. Tell me how to figure out the minimum voltage that I need. This is a great interview question or a great exam problem. Okay, well, wait. What's this voltage? It's going to be a constant. VGS. Remember, we're designing so our VGSs are fixed. That's how we select the device sizes and all that, right? What's the minimum voltage I have across here called? No, just from here to here, the source to gate voltage. It's called VSD SAT. That's the minimum, right? I got to stay above that. Righto? So here, on the left side, VDD min has to be greater than or equal to VSD SAT plus VGS. Does everybody see that? So just throwing some numbers in from our example sizes and currents, this is 1.05 and this was 0.25, so that's equal to 1.3 volts. VDD has to be above 1.3 volts. Pretty good, huh? Now what is it here? What's this voltage? VSG. So what is this voltage? Correct? And that's equal to what? Yeah, we just leave it like that. Okay, then what do I need here? VDS SAT. And I'm going to neglect the voltage drop across just for my estimate. So for the other side, I get the following. Has to be greater than a VSG plus a VDS SAT. So putting in the numbers, 1.15 plus VDS sat is 0.25 again in the example. And I say that, does everybody know what I'm talking about when I say the example numbers that I just used, like in the back of the book? I said, okay, well, let's just, so we don't have to calculate the numbers over and over again, let's assume that a basic design is size of, I mean, of course, the device size changes or whatever, these are going to change. But the device size is 10 by 2, and they bias them at 20 microamps, and then we get 250 for the VSD SAT, VDS SAT, and VSD SAT, and 1.05 and 1.19 because the threshold voltage of the NMOS is 0.8 and the threshold voltage of the PMOS is 0.9. Everybody see that? Any questions? So this is only for this current and this device sizes and this process. So I'm just throwing in some numbers because that's going to be what my sim is. So if I look at that here, that gives me 1.4, but I neglected this voltage drop, so I'm going to say that this is the dominant one, and VDD min has to be greater than or equal to 1.5 volts. That's what I'm going to look for. Any questions? So let's go look at figure 2016. And we're going to talk about the startup circuit in a moment, but for now we're just going to stick with this circuit. Now I'm going to hit run, and note I'm sweeping my VDD, and I estimated 1.4, 1.5, and I go check. And well, first, what ideally does this look like? This is plotting the current in ID1 and ID2. What should it ideally look like? Well, they should be equal, but also more importantly, they should be flat. Should be a perfect current source. So now I can use this V bias N to bias NMOS, the V bias P to bias PMOS, and they're not going to change the currents with the power supply voltage. I don't want my monitor getting dimmer if the power supply voltage drops. I don't want my cell phone to ring quieter or louder because my battery's draining. Everybody knows the battery's not at a fixed voltage, right? It's going to vary as it gets discharged. That's how they tell the capacity of the battery. Okay, I want it to stay fixed. I don't want those things to change. Okay, and then over here I see that as I get VDD below a certain value, the circuit can't function. So I'm going to pause now and ask you some questions. What is the M or the K, the multiplier? This is called a beta multiplier. What is the beta multiplier factor? No, what is it in this circuit? No, I got to multiply the beta up. What is beta? Kp times W over L. So if I multiply the beta up, how much am I multiplying this up here in M2? 4. How do I know that? Right there. 40. Here, 10. This one's 4 times wider. M is 4. Yay? We all good? Okay. Now, if I take, I don't want to use this transistor. This has been multiplied up. If I take this transistor right here, and I control E it, and then I come over here, and I say to myself, let's put a wire on here. Go like this, and then I hit label, and I go V bias N, and then I get the scissors out. What was the current? Roughly 20 microamps. And I go, let's say, I grab a resistor here. And let's go copy the VDD because I got to have some place to supply my current. I come over here. And let's just be fancy and call this Vx. And let's say I make this, how about 100K? And I ask you, tell me without thinking too deep or doing calculations, what's the voltage Vx? Okay, but what's the current flowing in M5? 20 microamps. That's a current mirror. This node is connected to this mode, so it's mirroring the current here. If I have 20 microamps, and I pull 20 microamps through 100K, what's the voltage drop across the 100K? 2 volts. So what is Vx? Be careful if VDD is 5. 5 minus 2 or 3. And then if I start to sweep VDD, what's going to happen to Vx? Start going down linearly. Or if I'm sweeping VDD up, it'll start going up. Yes? That's the temperature coefficient of the resistor. So let's go like this. Let's hit run, and then let's plot Vx. And then you see here above a certain value that the current will start going up. And at 5 volts, my voltage is, we said 3. So let's go to 5 volts, which is roughly right. Wait a sec. So, oh yeah, that's right. I'm at a VDD of 5 volts at the bottom. And then if you look at Vx, it's roughly 3 volts. So does everybody see what I'm doing here? You see how I'm changing VDD and it's keeping the current constant? That's why in my monitor I drew a 75 ohm load to ground, because if VDD changes, how does that change the voltage across the resistor? It doesn't. You don't believe me? I don't blame you. Let's prove it. Copy. All right, let's get the scissors out. I'll be sloppy here and just connect the wire, and I can label it. I won't be lazy. And then let's get our resistor here. And for the resistor, what's the voltage drop again? 2 volts. Let's call this Vy. How do you think Vy is going to change with temperature or with power supply voltage? Not going to change much. Come on, you little, get in there. All right, let's hit save, run. See how it comes up and is nice and flat as we sweep VDD at 2 volts. What's that? Yeah, it doesn't affect it. Your monitor stays the same brightness. Any questions? Does this make sense? Is this useful? Very useful if you want your circuits not to change with power supply voltage. Okay, so let's talk about this part over here because nobody has any questions whatsoever. Gabriel? Giovanni? All right. I don't want you leaving here and saying you didn't get your money's worth. Too late. I'm going to say it anyway, just because you told me not to. All right. Let's talk about why we need a startup circuit. This is called a self-bias circuit. So in any self-bias circuit, if you took 421, the band gap we designed, that was also a self-bias circuit, and there was a startup circuit in there, and I want to explain that to you now. So if you look at the following, which is the beta multiplier we just talked about, multiplying up the beta. I want you to, so why is a startup circuit? So startup circuit, I can tell you, it's like when you do like references, which is what the beta multiplier is, it's a reference. When you do a reference design, people focus on trying to get the currents the right values and the sizes the right. And then you know what always ends up being the problem in production? The startup circuit. Because that's like something you don't pay attention to, because it's like once it does its job, you don't care about it. Okay, I can't tell you how many times that's happened. The other one that is an issue that's discussed in the book is bonding this resistor out. That means connecting it to a pad and then bringing it off chip. It has a capacitance here that shunts the resistor. And this is an example of a circuit with positive feedback, but by putting a resistor here, you drop the gain, the positive feedback system, to less than 1 so that it's stable. But if you put a capacitor here now, it can peak the gain and it'll oscillate. I go through examples in the book about that. It's kind of an advanced topic, but it's in chapter 20 if you want to read about it. But I want you to think about the following. We know what our normal operating is. This is VGS. This is a VSG. We got current flowing in both sides. But won't the circuit work just fine if this is at 0 volts and this is at VDD? If this is at 0 volts, what's the current flowing in those two transistors? 0. Their VGSs are 0. And if this is at VDD, what's the current flowing in those two transistors? 0. So that's a valid state. There's two valid states, the one we just discussed and the situation where there's no current flowing. Does everybody see that? Okay, so what I'm going to do is I'm going to put a circuit called a startup circuit in here that will sense when I'm in this state, and it will leak a little current over here in order to snap it into the right state. And so let me try to describe that, all right? So let's say that I have a circuit here, and let's just draw, we don't know right now, but let's just draw a little switch. Let's say we drive this switch to VDD. Okay? That'll turn this transistor on, right? That causes a little current to flow. Well, can the current flow over to the gates? No, gates are going into a piece of glass. So it starts to drive this node up, starts to charge that node because that little current's leaking and pulling this node up. As this node goes up, what happens to the two transistors? They start to conduct the current. They get to where they start conducting the current. Then that gets mirrored over here. Well, now wait a sec. When I mirror current here, it has to be pulled through here, so that causes the current in here to go up. That's mirrored over here. Well, wait a sec. Now I have this current and this current flowing through here. It causes even more current to flow through here. That causes even more current to flow through here, more current to flow through there, more current to flow through there, and then this goes up even more. So it keeps going up until I get to the state that I described a moment ago. So now, how do I design this circuit right here? Okay, the way I'm going to do it, there's lots of ways, but here's one. Man, I have so many stories. I remember when, you know, in your phones, the cameras that are used in the front and back cameras, those are CMOS imagers. So before they used CCD devices, and CCDs you can't fabricate, they're a more expensive process. You can't fabricate them with standard CMOS. And back in the late 90s, early 2000s, the guy that was the pioneer, Eric Fossum, that pioneered CMOS imagers, owned a company called Pixtech. Wait, was it Pixtech? Holy crap, been 20 years, I guess. Anyway, he was at Caltech, and it's really hard to make money in electronics. So long story short, he made a deal with Micron, which is a big manufacturer of the memory chips I talked about up in Micron, because they could use an older process and reuse the equipment in the factory for making the cameras for the phones. And so we had to transition the cameras into the DRAM processes. So I went down to Pasadena when they were first to help out get this going, And one of the issues they had was with the startup circuit in a self-bias reference. And it was leaking too much, and it was causing the leaking. In fact, I put a homework problem in here. When this will help you out for your homework. When you look at the, you get a trace like this. So many homework problems. You get a trace like, you look at the current in the devices and it looks like this. Why do I always pick pictures that are on the bottom of the pages where I'm going to move this? You start to get the increase here. That's saying the startup circuit is leaking into the beta multiplier. You don't want that startup circuit to leak into the beta multiplier after it turns on. You want the beta multiplier to be totally independent, just like we described, independent of the startup circuit. So they were having this kind of effect on the startup circuit, and that was on the reference, and it was messing things up. So anyway, that was one of many issues. But we got them working, and then Micron spun that company off into Aptina. Anyway, all right. And my first PhD student at Boise State, this guy right, right here, Shangli Li. He now is the, let's see if we can pull it up. So he did his PhD in CMOS imagers with me at Boise State, and he's now the sensor characterization manager at Apple for their phone imagers. So, yeah, actually, as a side note, and I'll shut up, my last two PhD students were also in radiation hard and high sensitivity or high speed shuttered cameras for scientific experiments like the CERN Super Collider. And this is for taking like hundreds of thousands of frames per second images. So you can take pictures of like hummingbird flying or other things, real high speed, and then capture the image and then process it slower. So take like, you know, a sequence of real high speed pictures instead of the slowness that you have with the your normal phones. But they're pretty good actually from where they used to be. Anyway, so if I leak this on, it snaps into the right value. So now I need to design a startup circuit, okay? So here's how I'm gonna do it. Now, what was the point, or what's the important thing about a startup circuit? You want it to start up, but once the circuit's starting up, you don't want this in the circuit. You don't want it to be part, okay? So I go over here and I'm gonna ask you something now for your startup circuit. If this is not started up, what is the current flowing in this transistor? Zero. So what I'm going to do then is I'm going to connect it to right here, and I'm going to put a couple transistors here. You have to design it and characterize it. And if this is zero, these are gate during connected. What do these transistors pull this node up to? They pull it up to, yeah, the power, VDD. Right? There's no place for the current to flow. They will leak this node up to VDD. If it leaks up to VDD, what does it do to this transistor? Turns it on. But once it turns on and I've got current flowing in here, I pull the current through those two transistors. It drives this to ground or near ground or threshold voltage. What does it do here? Shuts this off. And so then my startup circuit starts it up and then it's out of the circuit. Does everybody follow that? Hisham? See, don't you like it? Educate me. Doesn't take much. Just ask Hesser. He educated me, now I know. I was watching YouTube and I was watching funniest game show fails. And it was Family Feud, and the family was asked, name a common name with the letter H. The guy said Jose, and I was like, And I'm like, that would be me. No, it wouldn't, but it would be if it was Hesser. I wouldn't mess up on Jose, but I would mess up on. Everybody's laughing, and he's like, "What?" And the family's like, "Yeah, great answer, great answer." And I'm like, "Oh, all right." Okay, so we all know why there's a startup circuit, right? Any questions about that? Okay, I want to do one more example. Who had a question?
I was gonna ask why there were two PMOSs.
Oh, I just picked some load up here that would be easy to pull to ground when this turns on. Because remember, it's got to be like a long L or something that is a big resistance. And if I put two PMOSs, I have a threshold voltage for each one. So I just need a load that once this is on, it pulls this to ground. It doesn't actually need to go to ground all the way, because imagine it's like a volt. Well, this is at a volt anyway, so the VGS is still 0, right? So I can pull it lower, I get a negative VGS, this shuts off. But I've seen situations where they don't design this right, and as they stress, like in testing, like they go up to 6 volts, this will go up, and then that'll cause this node to go up enough, and this will leak, and you'll start to get that current dependence. It's on your homework. So you're going to be like, I don't know why that's there, but now you know, right? Okay, so that leaks in, and you don't want the startup circuit leaking in. Like I said, you see right now, it doesn't do anything. Once it turns on, it doesn't do anything over here. But you don't pay attention to it, and then that's where all the problems are. You don't test it for the temperature and the threshold voltages and all that stuff. Now note, if I have 0 current flowing through here, what will this node leak up to eventually? It's 2 diode drops. These are gate drain connected transistors, are called diode drop transistors. There's no place for the leakage through these to go to, so it has to leak up to VDD. Does everybody see that? So it has to leak up to VDD, and then once this turns on, it pulls it down, and ideally pulls it to 0. So you want a heavy load there. It doesn't need to be it doesn't need to be something that pulls this up fast, because this is a DC circuit. So I just threw some load in there that I knew that once this is on for any values of VDD, this will stay near ground. Now, imagine you have these here. This VDD goes up. Eventually, this has got to go up too, because it's being pulled up by VDD. All right? Okay, so I'm going to, yes? Okay, so you agree once it shuts off that there's current flow, or once the beta multiplier turns on, that there'll be a current flowing in here? There's a current flowing in here, and I make this resistance big enough, that voltage drop across that from this current flowing in there will drive this node to ground. So wait, let me do it simpler. Here's 5 volts. Here's 1 mega ohm. If I ask you, what is this voltage? What's the answer? Wait, where does the current flow through the resistor? Wait, is there any place for a current to flow through the resistor in this circuit that I have right here? No. So what's this voltage? 5. Remember circuits 1, we said if there's no current flowing in a resistor, there's no place to flow. Both sides of the resistor have to be at the same value. Right? Now, imagine I put a 10 microamp current source here. What's the voltage drop across the 1 meg? 10 volts. Well, wait, I only got a 5 volt source. There's no way this can get pulled to 10 volts. So this will start to shut off, and this will go to 0. Right? It'll go down to 5 microamps. Here's the curve. It's going like this. I want to be up here at 10, but this starts dropping, and then I reach here to 5, and then it shuts off, and that's at 0. Any questions? All right, let's do one more example. I'm going to modify this because this is a quiz and homework problem, and I want you to have an easy life. I'm going to do another reference, but I'm going to change it up a little bit, and you're going to help me solve it. Change it up. Let's do the following. It's going to be the same principles that we went through already. With some multiplication. Okay? Whoops. What? Oh, am I? Hold on there. Now, how do I turn off the... I guess the easier answer is just don't put my arm on it. Okay, so first off, you're going to help me here. If I have a current and it's I, what's the current over here? You don't know? Assuming the rest of the circuit's in there, right? Anybody disagree with that? Because I made this m times wider, m of them in parallel. Okay, so then I come over here. And in this circuit, I'm going to make this Wn over Ln, and this one Wn over Ln, and they're going to be exactly the same size. Dun, dun, dun. I want you to derive an equation for I. You're going to help me. What can I say? You understand the NMOS are the same size now, right? Which one of those NMOS are the same size? Which one is going to have a higher VGS? M1 or M2? M1, why? It's got a higher current. What's the relation? It's MI. Okay, so what's the voltage drop across the resistor? It's the same exact thing. Yay, drummer? Wait, hold on, we're not done. It's not the same exactly. So what is VGS1? You're liking my class, aren't you, Hisham? You know what? I think I used minus V threshold earlier, and it should be plus V threshold. Boom, boom. Doesn't change anything. It's still the difference. I don't want you saying my notes are crap. Too late. All right, so this is 2I over Kp times W over L plus V threshold N times 1 over R equals I. Anybody agree with that? And would you agree now that I can write this as, pulling it, these cancel? I can write this as, I'm going to skip a step, tell me if that was a mistake. I'm going to write this as, I won't skip too many steps. Square root of 2I over Kp W over L R squared. And then times square root of M minus 1 is I. And then I can go on the next page. Any questions? Sony? It's good? So far, so good? All right. And then I can write this So I'm going to cancel the I, and this will be square root of I. Square both sides, and I get I equals 2 over Kp times W over L R squared times square root of M minus 1 squared. So can M be equal to 1?
You have no strip
Oh, it can't be if you want a current, right? Same thing in the other. And let's back up. Explain to me, just to make sure it's clear. Explain to me in simple terms why these two transistors can't be the same size. If they have the same current flowing and the same size, they got to have the same VGS. And if they have the same VGS, what's the voltage drop across R? 0. No current flows in the circuit. Similarly, if we go over here, and if these two are the same size, we have the same current, then we have the exact same question I just asked. These are the same size and I have 0 current voltage across the R. Okay, so now let's go look. I want to modify this real quick. And let's pick, how about, let me think. I want the same value, so I want this equal to 5. Square root of 5 would be 3, 9, 0, 2. That would be, yeah, let's pick this M equal 2. Let's say, I want to simulate it real quick. Shall we? So that would be square root of 2 minus 1. What's square root of 2? 1.41? Yay or nay? What's 1.41 minus 1? 0.41. What's 0.41 squared? 0.16. And let's wait, 0.17. And if I ask myself, how does that compare to the previous, which was 1 minus 1 over the square root of k squared? K was 4, so that would be 2. This is 1/2. That squared is equal to 0.25. So what do I expect? I expect if I use M equal 2 here, the current's going to go down a little bit because I only have 0.17 instead of 0.25. Let's find out, and then we'll do our quiz. Any questions? So let's pull up the circuit that we just looked at, which was 2016. And let's change this to M equal 2. And I probably have to go do the little, oh, it does show it. All right. And let's change this to 10. And we don't need confusion, so let's get the scissors out here. Get rid of these. And then it was slightly below 20. Now I'm guessing it'll be 13 to 14 microamps. Run. And we see that it's a little lower than I thought. Wait a sec, why is this one back up at 24 or whatever? It's like 12, I guess, up at 5 volts. Why is this current twice as big as this one? Yeah, because I set this to M equal 2 and this to 1. And if you go back, and M was 2, if you go back and look, that's exactly what I expect. One side's going to be twice as big as the other. Yay or nay? Does this make sense? Isham? All right. Christian? It's good. We ready for the grade booster? Let's do it.